Welcome back. That was a pretty long video, that first video, so I'll try to make it up for you by making this video a little bit shorter. Last time I talked about the basic concepts of remote sensing, passive remote sensing, active remote sensing. It's all about sensing or recording data measurements without actually touching the thing that you're recording from. Got different types of resolution that we need to worry about with this remote sensing information. Spectral resolution is the number and size of wavelength intervals that you're recording, and we call each one of those intervals of wavelengths a band, and the width of the band would be the bandwidth. So if we're recording 3 different wavelength intervals, we'll have a 3-band remote sense data set, and each band will cover a different interval of the spectrum. We go all the way from single bands, which just record one interval, to multi, to hyper, to ultraspectral, which of course has way many bands. Spatial resolution has to do with the smallest resolvable separation. So if we have 2 items on the surface of the Earth and they're separated by a certain distance, what is the minimum distance they can be separated by, such that each one is recorded as a separate pixel, a separate image, a separate piece of that remotely sensed data set. Temporal resolution has to do with how often we record the data. And you can imagine a lot of this stuff is satellite data. Satellites, depending upon the altitude that their orbit is at, are going to pass over the same spot on the Earth at some frequency, and so you can only get data from that satellite at that temporal frequency. Radiometric has to do with the number of distinctions in the data that we can record. So if we can record anything from 0 to 100 in intervals of 1, we can have 100 different pieces in that signal. If we can only go from 0 to 100 in intervals of 10, we're going to only be able to have 10 intervals in that data. Spectral resolution, again, that's the number and width of the bands. And so here you can see typical imagery, blue, green, and red bands. Those are what we can see in the visible part of the spectrum in there. And then we have near infrared. If we have 4 bands and our screens, our display screens, can only display 3 colors, because that's how many different types of phosphors the screens have, we need to decide, if we want to display the infrared, which color that we can see will display that infrared as. And so here we have a natural color composite, blue, green, and red, and this one we have an infrared color composite, and we have green, red, and near infrared. So the near infrared is being displayed as red, and that will come out as vegetation showing up as red in these things. This kind of shows you about spectral resolution again, what the widths of the bands might be, and with types of photography, what type of film can record which bands of the spectrum. This would be the natural color imagery. It's kind of hard to distinguish here, but this has got red, green, and blue in it. And if we want to look at this false color, which is the near infrared, is given the color red, then the things in the near infrared, which are going to be those vegetation things, are going to show up as red on this image. Spatial resolution, again, that's the minimum spatial separation that you can distinguish. So when we have small spatial resolution, here's ½ meter by ½ meter, we can distinguish between boats that are a certain distance apart. As the resolution gets larger and larger, we start to be able to distinguish less and less in the image, and at some point we can't really even tell that there are individual boats in the image, because the resolution becomes too high to be able to resolve the separation between adjacent boats in the marina. At some point we lose a lot of information, and we can't really tell what's going on because our spatial resolution becomes too large for us to distinguish what we need to be able to distinguish. This has to do with the geometry, the physical geometry of your sensor unit, and the key in the sensor unit is the focal length, which would be the distance from your lens, your focusing lens, to your sensor. So the greater the focal length, the larger or wider you're going to be able to make your sensor. Okay, can only pack electronics into such areas, so the wider you can make your sensor, the more electronics you can pack in. The further you are away from the ground, the larger the area you'll be able to cover, and the larger area will still have to fit on your sensor. So this sensor will be able to have a spatial resolution at this distance that is smaller than a spatial resolution that's out at this distance, because it has to cover a larger area. Temporal and radiometric, that's just straightforward what it sounds like. Temporal is how often you can collect information. This is what the Landsat satellites do. They record the same spot on the surface of the Earth every 16 days. So you can only get Landsat data that covers your one spot of interest for every 16 days. Radiometric is, again, the interval we're storing. If we store information in 7 bits of computer storage, we're going to only be able to store values between 0 and 127. If we store it in 10 bits of computer storage, we're going to be able to store values between 0 and 1023. So we're going to be able to get much finer resolution in the higher bit storage data than we are in the lower bit storage data. This is, of course, going to take a lot more space to store than this. When we get that, we get better resolution. This shows some of the more popular satellites. We have Landsat, NASA satellites. We have SPOT, GOI, and Digital Globe. These are commercial satellites, and so when you look at Google Maps or Google Earth or Bing or things like that, you're probably seeing commercial satellite images as opposed to the Landsat images. This column shows you the spatial resolution associated with the spectral bands that are in that sensor on the satellite. So for example, in Landsat satellites 1, 2, and 3, these are basically versions of the satellite, you have 79 meter spatial resolution in the 0.5 to 0.6 micrometer band. You get that once every 18 days. That's when the satellite passes over the same spot, and you're storing that information in 6 bits of computer storage. So these are the older satellites, and you can see that their spatial resolution was kind of high. You can see that their temporal resolution was kind of slow, and they didn't store that much information. Get down to the more modern ones, they can point those wherever you'd like. They're stored in 11 bits, and we're getting down to really fine spatial resolution. And there are satellites out there that we don't know about, that the DoD and others are flying, that can give us even finer resolution than these. Why does this resolution matter? Well, it matters because if you were interested in a certain aspect of the world, you probably are going to need a certain combination of spatial and temporal resolution, and maybe radiometric resolution, and maybe spectral resolution. So all the resolutions are going to be important to answer questions that you have associated with a certain area of interest. So if you're looking at climate, you're not that interested in getting things every day or every 10 minutes. You might be able to get things every year and still be able to get information about the climate. If you're looking at global climate, you might not need 10 meter resolution. You might be able to do 10 kilometer resolution. Okay? Likewise, for some of these areas of application, there is kind of a range of spatial and temporal resolutions that are going to fit the questions you'll want to ask in that area of interest. And if you find an area of interest that has something that has publicly available information from satellites, you'll be able to get publicly available information and answer questions associated with that area of interest. So in general, the free stuff that the government gets is out on this higher or larger resolution spatially, and the stuff that you pay for is the finer resolution. Okay, that was a quick through on different types of resolution. You can see where you're going to need to fit them to your area of interest and find data that has the proper combination of spectral, spatial, temporal, and radiometric resolution for your area of interest. Next time I'm going to talk about distortion and how we correct for distortion. You can imagine with all the geometry associated with this stuff, there's going to be distortion, and if we're going to put it on a flat map, we need to be able to correct for that distortion. So that'll be the next video. Tune in then.